So in the last class, we discussed about line integral, and today we are going to discuss about surface and volume integral. Okay, we already studied about the triple integral and the double integral, so this is look like same thing. So the next one is surface and volume. So surface means second integral, volume is triple integral. Okay. So simply I can write, suppose f is a vector point function, capital F is a vector point function. This is a vector point function. Then the integral, we call the integral is the integral double integral over the surface S f dot ds vector, or so ds is a if you write ds vector is nothing but a unit vector along the direction n cap into the magnitude is ds. So or we can write the double integral over s f dot n vector, that is we can write n cap is a unit vector. Usually cap means unit vector into the magnitude ds. So this integral is called surface integral, is called the surface integral. Surface integral of f, integral of f vector over the surface s, over the surface s. Okay, now we solve some problem, and then similarly we can define what is a volume integral. So simply we can write triple integral over the volume v. So if we take again f is a vector point function, the same thing, then the triple integral over v f dot dv is called the volume integral. Volume integral of f vector over the volume v, over the volume v. So volume is actually 3 dimensional. So even if you take, instead of vector point function, you can take the scalar point function also. Again we can define for scalar point function pi, so pi times dv over v. So this is also called integral value, volume integral of pi, the scalar point function pi over the vector over the volume v. Okay, now we solve some problem. So exercise, suppose if f vector equal to 4x I vector minus y square j vector plus yz k vector, evaluate double integral over s f dot n ds, where this s is a surface, where s is the surface of the region or of the cube. So surface of the cube bounded by, so x equal to 0 and x equal to 1. For y y equal to 0, y equal to 1, and z equal to 0 and z equal to 1. Now if you draw the picture, you draw the cube and you have to take the surface of the cube. Okay, suppose this is okay, this is z axis and this is some x axis and this is y axis. So x, y, z axis. Now x, this origin. So x ranges from 0 to 1, y also varies from 0 to 1, z also varies from 0 to 1. Okay, if you plot the picture, you can see that. So maximum this z value is 1. Okay, and you will get some cube. Okay, this is the length 1. Again you can get this length 1. Again from this varies z equal to 1 and this value is 1. Again this point we will get. So almost assume that this is a cube and then this one. So this is like cube. So you take the only the surface of the cube, that is our surface S. Now we have to find the integral. So usually we call some name. Okay, this end. So maybe we call this is A and this end is B and maybe this is C. This end is C and this is D and this is E and this is F and this is G. So there are 6 faces. Okay, so totally we have 6 faces in the cube. So what are the faces? First we list all the spaces. So from this right x side we have a G, D, F. Okay, this face. And then the another face is opposite side, the OBEC. OBEC, the opposite side of the x axis. That is another space. And then the y side we have a BETG. So this is another side. And then the opposite side for y axis, that AFCO, or we can take OCFA. That is another space. So another one is the bottom. Okay, bottom and then upper. So the bottom, what we have, OAGB. This is another bottom. Then the upper side is FCED. So totally we have 6 spaces. So we have to evaluate each spaces and then finally you have to sum. Okay, now first we have to find 1 by n. Okay, first we take AG DF. Okay, in the AGEF, look at the picture. This is towards x-axis. Okay, so therefore x should be maximum 1. So here x is 1. So if you take the further space in the space AGDE, DF. In the first space, so this space. Okay, so here x value is 1 and then the direction is x direction. Okay, so that unit vector should be I vector. So here x equal to 1 and the n unit vector here I vector, because we are seeing this face. Now what is integral? So double integral over this space, this surface AG df f dot n vector into ds. Okay, so here you can write here. So integral, only the variables are y and z because x is fixed. X is fixed at 1. So only y varies from 0 to 1. Z also varies from 0 to 1. So in f we have to substitute x equal to 1. So what is f? 4x z I minus y square j plus y z k. Okay, and then you have to dot with this n product. So n is nothing but just I vector. So what is f? I can write here. So f is 4x z times I vector minus y square j vector plus yk yz k vector. Now the formula is f dot n vector. N vector is I vector. If you dot with the I product, we get only this term. All the terms are 0 because I into j is 0, I into k is 0, I into k is also 0. Only I into I is 1. So we get only this 4x z. ds is nothing but actually only the variables are y and z. Therefore dy dz or dz dy. Okay, so better we can take dy. Now already we know how to integrate this. So this is z range. Here 4x is constant. Therefore 4x if you okay so I think so here x is 1, right? So already we take x is 1. So just we have 4z. Okay, so this is x because x should be 1 in this case. So we have 4z. And if you integrate with respect to y, we get 4z. If you integrate dy, we get y. And then upper limit is lower limit, we can substitute. So you get anyway 1. Therefore, again, what is the integration of z square by 2? 2 to cancel, we have 2 z square. And if you substitute upper limit, lower limit, we get 1 minus 0. Therefore, we get 2. Therefore, the surface integral of this space AGDF value is 2. Now we can take the opposite side. The opposite side means what? This A, E, B, O. Okay, if you take this space, in this case, what is the values of x? That is x is 0. Okay, x varies only in this direction. Okay, so all other this side is our x is 0. Okay, so if you look at that space, what is that? OBEC. So next OBBC in OBCE, I think so. EC in C. So in this direction, in this space, x should be 0. So this is opposite side to this x. So this is I vector. So this is opposite to I vector. Okay, therefore it should be minus sign. So therefore the n cap, the unit vector should be minus I vector. Now therefore the integral becomes double integral over this space OBCF f dot n vector dot ds equal to, so again here only again y and z are varying. Y range is 0 to 1, z value is also 0 to 1. Now if you again if you dot with this n vector, so the last the previous we get just 4 is 4x z is okay, 4x z is the x coordinate, but if you multiply with the dot product with the minus, therefore you get minus 4x z, but x is 0 here. Okay, so but one more thing is that the dot product should be what you'll get anyway 0, right? Why? Because if you write what is f vector is 4x z I vector. Anyway, don't bother about j vector and then k vector because you are going to dot product with I. Therefore these two terms are always 0. Dot with j, dot with k is 0, but here x is 0 because in this case x equal to 0. Therefore totally we get 0. 0 times dy dz, anyway you get 0. Okay, therefore the surface integral of this space is 0. Now if you take this space sorry, this maybe you can take some other color. So if you take this D, E, B, G, again t. So this is towards y axis. Therefore here y should be 1. And what is the n cap here? This is a arrow, is a direction to the y axis, therefore should be j vector. Okay, therefore you can easily find the that. Therefore y equal to 1, n should be t. So the next, in the space, what is that? I can write b g d e. In this case y is 1, the direction is n cap is j vector. Now double integral over this region f vector dot n vector into ds is, again x ranges from 0 to 1, z ranges also 0 to 1, but if you dot product with n, what is actually f? 4x z I minus y square j plus y z k. If you dot product with the j, only this term is not zero, all other terms are zero. Therefore we get minus y square into dx dz, because only variable is here x and z, because y is 1 fixed. Now if you integrate with respect to x, so anyway minus, you can take y square is constant, you can take outside, therefore y square, oh sorry, here y is 1 also, so no need to write this thing, so just y is 1, therefore we get just minus 1. So finally dx differentiation x, if substitute lower limit upper limit, you get 1. Again if we differentiate integrate dz, we get z, substitute upper limit lower is 1, therefore totally we can directly write minus 1. So in that space the surface integral is 1. Now you take the opposite side of this y axis, like this space. What is this? This region. This region opposite to this y axis. So in this case y is 0. What is the unit vector is opposite of this, that is minus j. So y is 0. Okay. Therefore what you'll get? So that region is in what is the region? Maybe I can take O A F C. So in this case y is 0. So the unit vector is negative of j vector. So now double integral over this space f dot n vector into ds equal to, again x varies from 0 to 1, z also varies from 0 to 1. Okay, if you dot with the j product, you get only the second term y minus y square, but y is 0, therefore this should be 0. So 0 times dx dz, therefore this should be 0. Now what are the remaining things? The bottom and then the upper side. Okay, if you take the bottom, z is 0. First you take the upper side. The upper side, so this region. So this region, this space, c z equal to 1 along the direction k. Okay. So similarly, if you take the bottom, z equal to 0. So first you take the upward direction. So in d e cf something, the upper side. So in this case z is 1, and then the direction should be z direction, that is k vector. Now integral over d e cf f dot n vector into ds should be, now x varies from 0 to 1, y varies from 0 to 1. If you dot with the k vector, you get the f dot k vector should be only the last term, you get y z. But here y is 1, sorry, z is 1, therefore just y dx dy. So anyway, first you integrate with y and then integrate with x. Therefore y square by 2. Okay, so you get 1 by 2. Simply because if you differentiate with the x, but x we get x, substitute upper limit lower limit we get to 1. So therefore anyway we get y square by 2. If substitute upper limit lower limit we get 1 by 2. Therefore, if you take the upper side, the region is 1. If you take the lower one, you get 0 because we have already y z. If substitute z equal to 0, that should be 0. So, therefore, if you take the bottom side, what is the bottom? OA GB. In the bottom, W integral over f dot n vector into ds should be 0. Okay, because z equal to 0 and the n cap should be minus k. Anyway, the direction is 0. Now sum all the things, you get the integral over the entire surface of the cube. So integral surface f vector dot n dot ds, sum of all the things. So if you sum everything, the first one is get 2, and then we get 0, and then we get minus 1, and then we get 0, and then you get here 1 by 2, and then here we get 0. So therefore this is actually 3 by 2 because this is 1 and the 1 plus 1 by 2 is 3 by 2. So the integral over the surface is 3 by 2. Okay. Okay, next we solve some problem to find the volume of the thing. So next problem. Exercise 2. Evaluate triple integral over the volume V del dot F into ds dv. Volume is V. If where F vector is x square I vector plus y square j vector plus z square k vector, where V is the volume bounded by the region, where V is the volume of the region enclosed by the cube. X varies from 0 to 1, y also varies from 0 to 1, z also varies from 0 to 1. If we take this cube, so directly we can find the integration. So first you find what is del dot f. So del vector is nothing but I vector into dou by dou x plus j vector into dou by dou y plus k vector into dou by dou z dot the f vector is nothing but x square I vector plus y square j vector plus z square k vector. So therefore you have to partially differentiate this. I dot I is 1, therefore 2x plus 2y plus 2z. So this is del dot f. Therefore the triple integral over V del dot f into dv is x value is 0 to 1, and then y value is 0 to 1, z is also 0 to 1. You can take 2 outside, maybe I can take 2 here. So therefore you get just x plus y plus z, and then dx dy dz. What is dv? So dv is actually dx dy dz. Now we can integrate. First with respect to z we can integrate, and then 1 by 1. Okay, so maybe you can change dz dy dx. You can do anything. Okay, because everything is a fixed one, constant is same thing, the way limits are. So if we with respect to z, we get xz plus yz plus z square by 2, upper limit lower limit. I can substitute remaining dy dx. If substitute x equal to 1, we get x plus y plus 1 by 2. Therefore 2 times integral 0 to 1 integral 0 to 1. If substitute the upper limit, we get x plus y plus 1 by 2. If substitute the lower limit, everything 0. Now integrate with respect to y. Therefore 2 times integral 0 to 1 xy plus y square by 2 plus y by 2 Okay, 0 to 1 dx. Now again, if you substitute x equal to y equal to 1, we get x plus, this is 1 by 2 and this is 1 by 2, therefore we get just 1 by 4. Okay, and if substitute lower limit, we get anyway 0 into dx. Now if we integrate with respect to x, we get 2 times x square by 2 plus x by 4, 0 to 1. So therefore 2 times 1 by 2 plus 1 by 4.
Sir, the
Yeah, what happened?
sir x plus 1, sir.
Oh, sorry. Oh yeah, 1 by 2 plus 1 by 2. Yeah, thank you. So x plus 1, and this will be x. Now if is about 2 times 1 by 2, that is 3 by 2, therefore we get 3. Okay, so maybe I can write, so substitute the upper limit only, we get this one, therefore we get 3 by 2, 2 to cancel, we get 3. So 3 is the volume enclosed by the cube. Okay, so now we have an important theorem, Gauss divergence theorem. So there is a relation between the double integral and then triple integral, that is the surface integral and then volume integral, that is Gauss divergence theorem. So maybe simply state the formula. What is Gauss divergence theorem? So whenever I use S, that is surface, and whenever I use V, that is denote volume. Okay. So F means vector point function. So the Gauss divergence theorem says the double integral over the surface F dot ds, or F dot n vector into ds, is same as triple integral over the volume del dot f into dv, where this volume is enclosed by the surface. Yes. Okay, so in the previous problem, the cube, you can take the inside cube. Okay, that is volume. If you look at the boundary of the cube, that is surface. Okay, or if you look at the some cricket ball, that is volume. Inside you can look at the volume. If I look at the surface, that should be sphere. Okay, open sphere. Okay, that's it. So if the volume V is enclosed by the surface S, then this is happen. Double integral over S, F dot n vector dot ds same as triple integral over V, this thing. Okay. Okay, then we have a next theorem. Another theorem for the simple deduction from Gauss divergence theorem is called Green's theorem. In that case, they will take some scalar point function. So the next theorem is Green's theorem. So Green's theorem actually is simple deduction from the Gauss theorem. Anyway, just you take the uh, conclusion. The integral statement is triple integral over V pi del square psi. Here pi and psi are scalar point function, minus psi into del square pi dv is double integral over s pi del v, or pi del psi minus psi del pi dot n cap into ds. Okay. So this is a Green's theorem. Actually, you will get this formula by take the vector point function f should be pi del psi. If you take f equal to this and then substitute in the previous Gauss divergence formula, you will get this. Okay, because here if you substitute instead of s f, we have substitute here del dot f is nothing but del dot pi del psi. So already we know that if you apply this, you will get pi del square psi minus and then del pi psi into del square. So you get the left hand side. Oh, sorry. You can dot product with here n. Okay, sorry. F dot, if you find f dot n vector, so you'll get anyway you can prove from that side, from the left hand side also you can prove from the right hand side anyway. So if we take the vector point function f equal to pi into delta psi, then you'll get this Green's theorem. Okay, therefore the Green's theorem is simple deduction from the Gauss theorem. You take the vector point function pi del pi, where pi and psi are scalar point function. Okay, so another one is harmonic function. So when we a function, scalar function said to be harmonic, del square pi should be 0. Okay, scalar function pi scalar point function pi satisfy the condition satisfying, okay, or satisfy the Laplace equation. Actually that is a Laplace equation. So satisfying the condition del square pi equals 0. Actually this del square pi is actually equal to 0 is actually Laplace equation. If pi is a solution of the Laplace equation, is called harmonic function. Is called the harmonic. So a function pi satisfied del square pi equal to 0, that such a function is called the harmonic function. Actually the equation del square pi equal to 0 is a Laplace equation. The solution of the Laplace equation is called the harmonic function. You will study in the complex analysis what do you mean by harmonic function. Now another theorem is that there are so many theorems. Stokes theorem is there, and maybe I can state what is Stokes theorem. Statement of Stokes theorem. Stokes actually, sorry, writing Stokes theorem.
Sir,
Yes, I'm audible.
sir, the screen was. Yes, sir, but the screen was stuck too long. Sir. Can you scroll?
So the Stokes theorem says again, simply state the statement. Single integral.
Okay, sir.
There is a relation between the line integral and then surface integral. That is Stokes theorem. Integral of C f dot dr, that is a line integral over the curve C, is same as the surface integral dot del cross f dot n vector into ds. Okay, so here S is a surface bounded by the curve. Suppose there is some curve C, we know how to find the integral over this curve, that is line integral. Suppose S is the surface bounded by this curve or enclosed by uh, this closed curve, then this is happened. S is a open surface. So S is a, so the Stokes theorem says a relation between a line integral and then surface integral. That is integral over C f dot dr equal to double integral over S del cross f dot n vector into ds, where this S is a open surface bounded by the closed curve. There is some curve C, closed curve, and if you know, don't take this much surface. If you take some closed open surface contained bounded by this one, bounded open surface bounded a closed curve. That is a thing. Is both are equal. So anyway, you should just remember this relation between the line integral and the surface integral. You can, this is a Stokes theorem, and actually we discussed all the important theorems. The important theorems are Stokes theorem, Gauss divergence theorem, and then Green's theorem. Okay. Anyway, so maybe the problems are similar. You can find a limit and then you can just integrate. That's it. Okay. So and then I just inform that how to change the, you know how to change the Cartesian coordinate into polar coordinates. Just to take x equal to r cos theta, y equal to r sin theta in the two-dimensional case. But what about the three-dimensional case? What is the substitution? Just I mentioned here. So from x comma y2, we change the polar coordinates r comma theta. What is the substitution you have to take? X equal to r cos theta, y equal to r sin theta, the two-dimensional case. So same thing here. Suppose we have to change the polar Cartesian coordinates x, y, z to r theta some pi. Okay, what is the substitution? You have to take x equal to r sin theta cos pi and y equal to r sin theta sin pi. Okay, sin pi. Z equal to r cos theta. Okay, so this is the spherical coordinates, spherical polar coordinates. Polar coordinates. Okay, so here actually the r always radius, okay, is lies between some 0 to, depending upon the sphere. Okay, sphere of radius r means I can take, maybe I can take some number, okay, some number 4 or something radius, and this theta varies from 0 to pi, and then this pi varies from 0 to 2 pi. Okay, so this is the limit for theta and pi. So if we take some sphere of radius radius 16, then r should be less than or equal to 4, because radius in general equation is x square plus y square plus z square equal to r square, sphere of radius r. So therefore r, okay, suppose I'm taking 16. So in this case radius is 4. The radius varies from 0 to 4, theta varies from 0 to 5, and then pi varies from 0 to 2 pi. And then what is dx dy dz? So here dx dy should be r times dr d theta. Here what is dx dy d theta, sorry, dz should be r sin theta into dr d pi d theta. So dr d theta d pi, you have to multiply into the r sin theta, sorry, r square sin theta. It's the only thing you should know. So once you know this transformation, you can some hardest problem you have to change into this theorem. Maybe anyway, I quickly solve one problem using the divergence theorem. So the divergence theorem says the relation between surface integral and then the volume integral, and then the Stokes theorem's relation between the line integral and the surface integral. Anyway, so exercise, evaluate triple integral or double integral over the surface f dot n into ds, where what is f? F vector equal to 4xz. I think already we solved this problem, same problem, but only changing the boundary. Okay, this is the f vector, and S is a surface bounded by the cube. This is the surface of the cube, but the cube sides are x equal to 0, x equal to 2, and y equal to 0, y equal to 2, z equal to 0, z equal to 2. So if you directly find the integrate, you got to find all the 6 spaces and then you have to sum. But if you use the divergence theorem, so you can find the volume. You can use the volume, right? So by solution, by divergence theorem, so we know that the integral double integral over s f dot n vector into ds, it should be triple integral over v del cross f, del dot f into dv. So this is the Gauss divergence theorem. Now here v is the volume inside this surface. Okay, so we know that there are everything is variable. Now x varies from 0 to 2, y is also from 0 to 2, z also varies from 0 to 2. What is del dot f? So f is I think 4x z I. If you take the dot product, okay, so y square j plus y z k. Okay, so if you dot with uh, this, you have to differentiate this partially with respect to x, therefore we get 4z, plus differentiate this with respect to partially with respect to y, we get minus 2y, and differentiate this partially with respect to z, therefore we get just 2y. Okay, into, you start with the okay dz or something, dz dy dx. Am I correct? Yeah. Now anyway, this 2y minus 2y plus 2y, we can simply write minus y. Therefore 4z minus y. Now if you integrate with respect to z first, so integral 0 to 2, integral 0 to 2, if you integrate with respect to z square by 2 to cancel, we have 2z square minus yz 0 to 2 dy dx. If substitute the upper limit, lower limit, 0 to 2, 0 to 2, 4 minus 2 y, because substitute z equal to 2. The lower limit anyway is 0. Now we have to integrate with respect to y. Therefore we get 4y minus y square. So it is 0 to 2, 4y, y square by 2, 2 to cancel, we have y square 0 to 2 into dx. So you get 0. I did any mistake here. So what is that? Oh sorry, this actually 4 into 2 8, right? because already here z square is 4. 4 into 2 is 8. Sorry. So therefore this is actually 8y. So now since substitute 2, this is 16 minus 4, therefore it's 12. Therefore integral 0 to 2, 12 dx. So therefore 2 into 12, therefore 24. So therefore you can directly write now. Therefore the surface integral is 24. If you directly find, you have to find the all the 6 spaces and then you have to sum. It will take time, but by Gauss divergence theorem, we can simply take the triple integral, that is a volume integral. You can easily find the solution. Okay.
Sir,
Yeah.
here how did we find? Like, how did they only take 4z minus y? Sir? Can you say that once again?
Because no, 4 is it? No, just you this one, right? You are asking why you are
Yes, sir.
taking.
The integral.
You got to take the dot product.
Yes.
You take the dot product.
Okay, okay.
So delta f, right? So you have to differentiate this partially with respect to x. What you'll get, just you get 4z. Plus you have to differentiate this with respect to y, but already we have minus. Therefore differentiation of y square is 2y. And then if you differentiate this partially with respect to z, therefore just y is constant. If you differentiate z, you get 1. Now you can cancel 1y, therefore 4y minus 4z minus. That is the meaning of del dot f.
Okay, sir.
You have to take the dot product and then sum. Partially you have to take dot product. The first term you have to do dot product with the x and then second y and so on. That is the definition. Okay, this is some. These are the applications of divergence theorem. Okay, so maybe similar problems, all are similar problems. Maybe you can, once you find the limit, you can easily solve the problem. Okay, so these are all things in the vector calculus. We'll try to solve other problems in the next class. Okay, now we start the class.